So without further ado, it gives me great pleasure to introduce Martin, who will open our academic learning today. Martin is Professor of Gravitational Astrophysics and Cosmology in the School of Physics and Astronomy at the University of Glasgow, where he's also head of school. Martin completed his PhD in the Astronomy Research Group at Glasgow and was a research fellow in the Astronomy Centre at the University of Sussex from 91 to 96, before being appointed a faculty member at Glasgow in 98. In 2011, Martin was elected a Fellow of the Royal Society of Edinburgh in recognition of his contribution to research, teaching and the public understanding of science. In January 2015, he was awarded an MBE for services to public engagement in science in the Queen's New Year's Honours List. In 2015, he was also awarded the Royal Society of Edinburgh's Senior Prize for Public Engagement. As a member of the LIGO team, Martin was awarded numerous international prizes, including the 2016 Special Breakthrough Prize for Fundamental Physics, the Physics World 2016 Breakthrough of the Year, and the President's Medal of the Royal Society of Edinburgh. Martin is a passionate enthusiast for public outreach and is the current chair of the LIGO Scientific Community's Education and Public Outreach Group, and conducts many additional outreach activities as well. As if that wasn't enough, Martin is also currently the chair of the Institute of Physics in Scotland. And with that, I will hand over to Martin.
Good morning, everyone. It's a great pleasure to be here, to be asked, great honour as well, to be asked to do the very first lectures in SUSSP73. I've been involved in running some SUSSP meetings in the past, so I know how hard the organisers have worked in pulling everything together. So it's quite a relief, in fact, to be asked to just do 4 hours of lectures. You might think that sounds like a hard job to do, but it's nowhere near as hard as how all these people have been working and putting the preparations together. The first SUSSP I was involved in was in 2000, and it was in Blair Athol in Scotland. Beautiful countryside, but the real drawback to doing it inland is that we had that Scottish phenomenon, the midgie, to contend with for 2 weeks. So I'm hoping that in 2 weeks in St Andrews, you might have some rather unpleasant weather to deal with, but at least you won't have too many midges to contend with. So, what am I here to talk about this morning? Well, Christian mentioned that I'm currently the chair of the LIGO Scientific Collaboration, Education and Public Outreach Group, but I'm going to talk about that after lunch. This morning, I'll be concentrating much more on introducing the broad theoretical themes of the whole school. And I'm charged with introducing us to general relativity and some of the basic detection principles for gravitational waves. And I'm minded that we've got quite a mixed group of students here. There'll be some students who are already, perhaps in the second or even third year of their PhD, they might already have got their heads round a lot of difficult and technical theoretical material, but there may be other students who are nearer to the beginning of their studies and perhaps have not yet done a course in general relativity. So maybe I should check that. How many people have done a course in general relativity before? Right, so almost everyone, but not everyone. Even for those who have, I think it doesn't do any harm to be reminded of some of the key ideas of general relativity from quite a basic starting point. And in fact, what I'm going to do is spend a little time also looking at special relativity and try to remind you, or indeed, if you've not encountered it before, introduce to you the idea that general relativity came from Einstein's work on special relativity. And if you are already familiar with all of that, then you can view this as a gentle introduction to the 2 weeks, that your first Monday morning engagement with the lectures is just reminding you of lots of things that you already know. But I suspect that for many, and even if you've done a course in GR before, that it will be useful to get this gentler introduction before we tackle some of the more advanced material in the lectures that follow. So you already heard who I am. Let me just get the laptop up on screen. Heard a little bit about who I am, and in particular the fact that I am currently the head of school in Glasgow University. So in some sense that means I follow in a very long and illustrious tradition. So most notable name of which is Lord Kelvin himself. So we live in the Kelvin building in the University of Glasgow. St Andrews is an even older university than Glasgow. It was the first one founded in the UK in the early 1400s, whereas in Glasgow's case we had to wait until 1451 before we were founded. Glasgow's the fourth oldest university in the UK. So Lord Kelvin doesn't go back quite that far, but he lived in the latter years of the 19th century and died in the first decade of the 20th century. And in that sense, he lived in an era that predates many of the developments that we're going to discuss today and throughout the following 2 weeks. He lived before the revolutions in relativity and quantum physics that would transform our understanding of physics in the 20th century. So although Kelvin made many crucial contributions to the development of physics, in some sense he does feel, from this modern 21st century perspective, as belonging to an era that has long passed. And perhaps that's reflected in a statement that's been attributed to Kelvin. I've never been able to definitively determine if this really was Kelvin that said it, but it feels like something he might have said because it reflected views that were prevalent at the time that Kelvin was around during the second half of the 19th century. It's alleged that Kelvin once said around about 1900 that there was nothing new to be discovered in physics now. All that remains is more and more precise measurement. So maybe Kelvin didn't say that, but as I said, it feels like something that might have been said around that time. Indeed, it's been claimed by other sources that this statement was attributed to Albert Michelson, of whom more later, and we'll hear about Michelson interferometers in great detail later in the course, later in the summer school. In fact, the only truly reliable source I've been able to find for a similar sort of phrase was the PhD advisor of Max Planck, who, it's reported in a few sources I've been able to track down, said to Max Planck when he was trying to advise him on what he should work on for his PhD, the phrase was, in this field, almost everything is already discovered, and all that remains is to fill a few holes. So I'm going to adapt that phrase of Max Planck's PhD supervisor a little bit. I'm going to say that all that remains is to find a few holes. And of course, that's what we have now done. So it seems a very timely way to look at the context of a SUSSP school in gravitational wave detection, gravitational wave astronomy, to begin, of course, by just briefly reflecting on what we have detected. So it was a great privilege to be part of the planning for the announcement of the first direct detection of gravitational waves that happened in February 2016. It's probably the busiest 6 months of my life, but very richly rewarding. And what we detected was the merger of two massive black holes more than 1 billion light years from the Earth. Of course, it didn't stop there, and that's really one of the main themes of this 2-week summer school, is that the story of gravitational wave astronomy doesn't stop there. It's like when Galileo first looked at the sky through an optical telescope and he saw the craters of the moon and the moons of Jupiter, and he could have said, well, that's all very interesting, I think I'll stop now. But fortunately he didn't. And of course we don't want to do that with gravitational wave astronomy either. So we subsequently detected GW 151226, an event that reached the Earth on Boxing Day, UK time. And I remember very well the moment that evening after we'd said goodbye to some visitors that had come for dinner, and I made the fatal mistake of saying, I wonder if I got any emails today. And then the whole process of preparing for the announcement of another gravitational wave detection began again. But in fact, it was June of 2016 before this second event was announced. And then many of you will know, indeed many of you were involved in, the third detection, which was announced on June 1st, 2017. And I was actually in St Andrews that day, not in this lecture theatre, but in the room across the way, because I'm external examiner for their undergraduate programmes. And our Board of Studies meeting, at which we awarded all the degrees, that ran on past the time when the press conference was about to begin. So I was nervously checking the LIGO website to make sure that the updates had happened when they should. And sure enough, this appeared on the LIGO website at the appropriate time on June 1st. And the person sitting beside me, Hongsheng Zhao, one of the faculty here in St Andrews, who of course doesn't work in gravitational waves but is very interested in what has been happening, well, he was very sharp-eyed because he just looked over and said, "That's a new one, isn't it?" So he recognised that the trace, the strain signal, which we had put on the banner of our website, was in fact a new third confirmed detection. So we call this one the Enterprise event loosely because it's 1701, and that of course is the NCC number of the Starship Enterprise. And this is a theme I'll return to this afternoon. So this morning you're going to get straight science, but in the afternoon, when I briefly look at some of the outreach work that we do within the LIGO collaboration, and encourage you to think of ways in which in your own studies you could get involved in a little bit of education and public outreach, one of the themes I'm going to emphasise is that we are never too afraid to link the hard science to just a little bit of science fiction, because it's an excellent way to engage the public with the fascinating science that we're discovering, and indeed to make them see that yesterday's science fiction can quite rapidly become today's science. So, that's for later. For this morning, as I said a few minutes ago, I'm going to try to review the basics of special and general relativity and pave the way for the lectures that will follow. So Sathya will take over from me. I think Sathya's on tomorrow. Peter, do you have some lectures this afternoon?
Tomorrow.
No, so tomorrow. So I think it's basically just me today, but then Sathya and Peter will take over tomorrow. So my goal is to get us to a point where we have a good feel for what gravitational waves are, in terms of the mathematics from which they emerge, the mathematics of general relativity. Now, clearly in only a few hours, it's going to be impossible to cover general relativity in great depth. So for those who've not studied general relativity before, this is why recording the lectures, I think, is very important. It's easy in a few hours to give you a qualitative sense of what general relativity is about. Indeed, we routinely do that in education and outreach lectures. The kind of phrase that we use is this one, attributed to John Wheeler: space-time tells matter how to move, and matter tells space-time how to curve. This is linked to a metaphor that is very frequently used in describing general relativity. I'm sure everyone here has encountered this metaphor before. We think of space-time as a stretched sheet of lycra or rubber into which you drop a massive object. It causes that space-time sheet to curve. So that's fine at the level of education and outreach lectures, but we want to move beyond that. We want to give you a sense of the underpinning mathematics that describes that curvature. And also, equally importantly, some of the physics that helps us understand where that curvature comes from. So the clue to that is, of course, in Wheeler's statement: matter tells space-time how to curve. So what is it about matter that generates that space-time curvature? How do we describe in detail, in quantitative detail, that relationship? Well, that is where the mathematics gets a bit complicated. So the mathematical statement that corresponds to that qualitative phrase of John Wheeler is basically Einstein's field equations. You've got matter on one side and energy, and you've got space-time curvature on the other. So John Wheeler's statement says that there's a fundamental connection between the distribution of matter and energy and the presence of space-time curvature. But in order to describe that connection, in order to describe that relationship, we need to introduce some mathematical concepts that some of you, if you've not studied general relativity before, will probably not be familiar with. So that's going to take some care, but we're not going to get too bogged down in the mathematical details because firstly, we have only a few hours, and secondly, we want to put the focus on the physics that's driving it. But in order to help you make more sense of the lectures that will follow, we will introduce some of the mathematical notation and the mathematical principles that give rise to these field equations. In particular, you may not have encountered this sort of notation before, where we have multiple indices denoting the components of what we call tensors. So one of my main jobs before the coffee break is to get us to a point where we have at least some sense of what tensors are and how they relate to the geometry that you've been studying really probably since high school, the geometry of vectors. So the way I'm going to approach this is probably not to the satisfaction of the mathematical purists, but it is an attempt in a very short time to build on what you probably already know well and show how that, with a little bit of extra mathematics, can give us the Einstein field equations. So general relativity is the theory that we use to describe the generation and indeed the observation of gravitational waves. And general relativity, captured by these beautiful field equations, has been widely recognized as one of the greatest scientific achievements of the 20th century. Indeed, Albert Einstein's great friend Max Born described it in these terms. He said it was the greatest feat of human thinking about nature, the most amazing combination of philosophical penetration, physical intuition, and mathematical skill. Now, of those three pillars, I'm not sure how much I can convey in just a few hours. I've already said I'm going to try and cover a little bit of the mathematical skill by introducing you to the ideas of tensors. But I think, most of all, I would really like to think that I will get somewhere with the physical intuition part. Because I'm sure you're probably all aware that gravitational waves, by the time they reach us, are incredibly weak. And that's why the detection of gravitational waves is such an incredible technological achievement. And later lectures will describe the technology required to detect them. So I think to give you some physical intuition as to why gravitational waves are so weak, that's one of the other things I'd like to do. That will be after coffee, but hopefully before lunchtime. So basically my goal is to introduce the mathematics of tensors, to walk you through some, at least, of the details of how gravitational waves emerge within general relativity, and to give you a sense of how strong the gravitational wave signal from astrophysical sources might be. And then I'll pass on the baton to Sathya and Peter and others who will take it from there. So why are we bothering to have a series of lectures about general relativity and gravitational waves? Well, aside from the very obvious fact that we've now detected gravitational waves, so it's a very topical subject, the other great achievement so far of our analysis of those gravitational wave detections is the recognition that so far Einstein's GR passes the test with flying colours. It provides an excellent description of the mathematical waveforms that we have observed. In other words, a comparison of our observations with the predictions of general relativity turns out to be very satisfactory. As I'll describe this afternoon when I focus for a little time on our education and outreach efforts, but it's worth mentioning this now in the context of the success of testing GR. Just like SUSSP73 has its own Twitter account, so does LIGO. At LIGO, we now have 45,000 followers. The day before the detection announcement, we only had 2,000. So finding something has made a big difference there. We've got a lot of followers. And we wanted to think of some good hashtags for the first detection announcement. And we went with hashtag Einstein was right. In fact, Barack Obama even retweeted that with that hashtag. So far, President Trump hasn't paid any attention to our LIGO Twitter account. Maybe that's a good thing. But we did think very carefully about that, because in a way, perhaps the more correct hashtag would have been hashtag Einstein isn't wrong yet. But that's a little bit more unwieldy when you've only got 140 characters to use. But the serious point is that we are very much in the business of testing GR. We want to test it to breaking point, you might say. But so far, the data have not done that. The confrontation between the theory and observations thus far has led us to conclude that GR passes that test. So there's a couple of aspects of that which I think later lectures might explore. One can look at different approximations to GR, what we call post-Newtonian approximations. I won't cover any of that this morning, but I think it will be developed by other speakers later. And then one aspect that I hope that there's the means to cover a little bit in future lectures, or maybe we can discuss in panel discussions, is linked to questions that people often ask in public talks. They say, well, does the LIGO detections tell us anything yet about quantum gravity? Because general relativity isn't the full story. We expect that somewhere down the line we might develop an even better theory of gravity that combines the elegance of general relativity as a field theory, a smooth description of space-time, with the recognition that actually space-time is almost certainly quantized, like everything else is in the physical world. And so far, our observations are only scratching the surface of that particular question. One of the ways that we've been able to attack it is by asking the question, is the graviton the quantum counterpart of gravitational waves, just like photons are the quantum counterpart of electromagnetic waves? Is the graviton, does it have any mass? Is it massless? And if it were massless, like the photon, that's significant, because that's, again, consistent with the GR theory, and it would lead us down certain paths in terms of extending GR to a quantum gravity description. And so far, we've been able to put some limits on the mass of the graviton, expressed equivalently in terms of the wavelength, the Compton wavelength of the graviton, but you can see that they're inversely proportional to each other. So in other words, if the graviton is massless, then its Compton wavelength should be infinite. And what we've been able to do so far, and this is actually from a paper from early in 2016, I think if I recall there's an updated version of this graph now, taking into account the second and third detections. But the bottom line is we've been able to establish that this Compton wavelength, if not infinite, is at least very, very large. So that's two examples of where the question, does general relativity really fit, that we tried to capture in that hashtag Einstein was right, have already had some quantitative answers, all of which has led to Einstein looking pretty happy. But as I emphasised, this is an ongoing question, and we'll be striving to subject future gravitational wave detections to ever more rigorous testing of whether GR is indeed the correct description. So, for the moment, GR provides an excellent description of the observations, the gravitational wave astronomy observations that we've made. So therefore, studying GR as a precursor to the more technical material that will follow would seem worthwhile. So what am I going to try to cover? So in the remainder of this morning, I'm going to take us through these topics. Somewhere around the coffee break, I will have got us, I hope, to a point where we've shown where Einstein's equations come from. And then after the coffee break, we'll look at specifically where the wave equation for gravitational radiation emerges from those equations. And the coffee break, to just mark your calendars. We are scheduled to stop for coffee at 11:15. But what I'll probably do is have a short stop about 10:15, 1 hour in, to just give my brain a couple of minutes to recharge and reboot before we start again. I'm hoping everyone can hear me okay. I'm not using a lapel microphone, mainly because I don't have a lapel, but also because we're recording on this microphone that's linked to the video recording. Whether you'll still be able to hear me at the end of 4 hours of lecturing today is another question, but we do have a lapel mic that I can wear if needs be. So we're going to try and cram quite a lot into, well, it's now less than 3 hours, but the remaining 2.5 hours or so. And the slides that I've got, they're really nothing more than just highlights, because as I was explaining before, if you've not met GR before, then even 2.5 hours is just going to be enough to scratch the surface. But hopefully it will give you a suitable foundation to help make sense of the lectures that follow. And we'll try to make these available as quickly as possible, both the lecture slides, but also a more comprehensive set of lecture notes based on a lecture course I give in Glasgow, and indeed have given in a number of other locations around the world. And these notes are more than 90 pages. So they might provide a more long-term resource that you could use to help you understand the mathematical complexities of general relativity. So hopefully none of that strikes you as too daunting. If the prospect of spending the next 2.5 hours doing general relativity strikes you as not the best way to spend a Monday morning, then I remind you of a quotation from Albert Einstein himself. Albert Einstein's view in the matter was that the hardest thing in the world to understand is the income tax. So I hope that by the end of my lectures you will agree with Einstein's statement. So let's begin with thinking about the foundations of general relativity. As I said, the foundations really are in Einstein's special relativity. So as I'm sure most of you will know, he published a series of key papers in 1905, what really made Einstein's name. And some of those papers were on the nature of space and time. And in special relativity, what Einstein was seeking to do was to formulate the laws of physics in a manner that would be valid for all inertial observers. So what do I mean by an inertial observer? I mean an observer who's moving at a constant velocity with respect to another observer. So it's very much already thinking about, the clues in the name. It's called special relativity. The theory is all about how the laws of physics are formulated in a manner that's relative to another observer. Now, it's not the case that Einstein was the first to approach it in this manner. In fact, if you go all the way back to Galileo, and indeed Newton, and in some sense what you might regard as everyday common sense, then we do apply some idea of the relativity of motion to our everyday common sense. So basically working out how things look to different observers involves following a set of simple rules. Those rules are defined in what we call reference frames, and one might consider two reference frames which are coincident with each other at some time t. So the dash denotes coordinates in the other reference frame, the undashed denotes the coordinates in the original reference frame, shown by the black coordinate axes and the light-blue coordinate axes. So Galileo, he applied himself to this problem to think how measurements of length and indeed measurements of velocity would be affected when you transform from one reference frame to another. So to put that in a kind of modern context, if you were sitting in this red car, in its rest frame, meaning an inertial frame that's travelling along with that car, if it happens to be driving along a road, then you can still define a reference frame in which that car is at rest. But then in that frame, along comes a blue car, which overtakes the red car. But viewed from the blue car's rest frame, it will look to the driver of that car as if the red car is travelling in the opposite direction and passing by, going from right to left. So Einstein had this framework to start from, but he basically realised in developing special relativity that it didn't work. It works approximately in our everyday common sense experience of the natural world, but in reality there are different rules from the Galileo rules that relate different observers' reference frames. And one of the ideas that led Einstein to that realization, if I'm allowed to be a little patriotic here, is very firmly due to the Scottish physicist James Clerk Maxwell. Most people in the world of physics would recognise Maxwell as really up there with Einstein and Newton as the most significant and important physicists of all time. And Einstein himself recognised that. So I thought it was worth just linking the work of Maxwell, which many of you, even if you've not studied relativity in great depth, perhaps in your undergraduate degrees, you've done courses on electromagnetism, you've done courses on light. James Clerk Maxwell, in 1865, published a seminal paper which established the electromagnetic spectrum. It established the idea that light was a phenomenon associated with changing electric and magnetic fields. And that led him to postulate that when electric and magnetic fields are changing, what happens is that it generates a wave of light, a wave of electromagnetic radiation. So there were a set of equations that James Clerk Maxwell codified, building upon work of previous decades of physicists. So he didn't come upon all of the equations himself, but he was the first person to put them all together in this manner. And one way we can write those equations, not the usual way, normally they're written in terms of first time and space derivatives, but we can take those four equations and turn them into two, which express the second spatial derivative of the electric field in terms of the second time derivative of the electric field, and do the same for the magnetic field. And the four equations that these two equations came from, those four equations involve two constants of nature known as the permittivity and the permeability of the vacuum, epsilon naught and mu naught, respectively. And one of the most remarkable things about Maxwell's work was the insight that he came to realise that these four equations that we nowadays refer to as Maxwell's equations, that they gave rise to these two, which basically take the form of a wave equation. And in that wave equation, the c here denotes the speed of the wave. But the c could be expressed in terms of these two fundamental constants that you could measure in the laboratory by doing experiments involving electricity and magnetism. And the thing that impresses me most about this was Maxwell realising that this constant that comes out of the mathematics, the fact that you get a speed of a wave, this constant agreed spookily well with the speed of light that astronomers had been attempting to measure. Okay, in the mid-1900s, not with the same precision that we can measure today, but well enough to make Maxwell realise that this surely couldn't be a coincidence. So what he'd done was he'd taken the mathematics of electricity and magnetism, the mathematics of changing electric and magnetic fields, shown that that gives rise to a wave equation, and then in turn shown that the wave equation involved a constant denoting the speed of the wave, which was fundamentally connected to these constants associated with electric and magnetic fields. So all of that convinced Maxwell that when electric and magnetic fields change, that it was no coincidence that the speed of the waves matched that of the speed of light. It convinced him, in fact, that that's what light was. It was an electromagnetic wave associated with changing electric and magnetic fields. But what was that electromagnetic wave moving through? Maxwell never really fully answered that question. In 2015, we celebrated International Year of Light, 150 years after Maxwell's paper, and I was asked to take part in a BBC programme to celebrate Maxwell's achievements, so I thought I'd better go back and actually read properly some of the original Maxwell papers. Believe me, that took a long time. They're incredibly detailed. Beautiful pieces of writing, but very, very detailed. And in it, it gave me some insights into Maxwell's thinking about the nature of space itself, the fact that light was propagating through empty space. Was it really empty? How can something propagate through empty space? So Maxwell had his own ideas on that. But again, these aren't lectures about Maxwell, so let me leave that to the side and jump forward a little bit now to several decades after Maxwell died. If we jump forward to about the turn of the 20th century, then we're around the time when others were trying to answer this question of what is it that light propagates through. And again, many of you I'm sure will know that Albert Michelson and Morley, they devised an experiment to try to measure the speed of light coming from different directions. So their reasoning was that if light needs some medium to propagate through, known as the luminiferous ether, then one ought to be able to detect the motion of the Earth through the ether, applying essentially the Galilean principles of how to transform from one observer to another, by looking at what happens when light propagates towards the Earth from distant stars in different directions. Again, an analogy that I'm sure many of you will have encountered before. Think of this like, for example, a swimmer who's swimming from point A to point B in the same direction and then in the opposite direction to the flow of a river. And then contrast that with another swimmer who goes from point B to C, but this is across the direction of the river flow and back. One would expect that it will not, even if the swimmers, with respect to the local water that they're moving through, even if they're moving at the same speed, because of the river flow, in a global sense, it will take the two swimmers different times to go from B to A and back, and to go from B to C and back. So that was the idea that Michelson and Morley were trying to exploit. But they detected absolutely no ether drift. It seemed, therefore, as if light was not following Newton's and Galileo's rules. So in a way, the seeds of that were already there in Maxwell's equations. So those equations that we saw before, that Maxwell could turn into a wave equation for the magnetic and the electric field. Here again is a little bubble coming from Maxwell. Light is a wave caused by varying electric and magnetic fields. But then Einstein comes into the picture and approaches it completely differently. Approaches it by asking a deep philosophical question that would open the door to special relativity. What he wanted to know was, well, yes, if light is a wave produced by changing electric and magnetic fields, what would it look like if I could travel alongside that light beam? Would it still wave under those circumstances? Or another way to think about it is like this. It's a rather loose analogy, but it's always helped me to understand what's going on. We can loosely think of electric fields associated with static charges and magnetic fields to be associated with moving charges. But as we transform from one reference frame to another, who's to say who's static and who's moving? Remember the red car and the blue car. So if that's the case, if the notion of who is static and who is moving, what is static and what is moving, if those need to be thought about more carefully when we transform from one frame to another, what does that mean for Maxwell's equations? Doesn't it mean that Maxwell's equations will take a different form, potentially, when you look at them in one frame compared to another? That idea troubled Einstein a lot. And indeed, the beautiful thing about Maxwell's equations was that as Einstein developed his version of the transformation equations, building on the work of people like Minkowski and Lorentz, then the realization was that that would preserve the structure of Maxwell's equations. They would indeed look the same to different observers moving in different inertial frames. So what all of that led to was the fact that the speed of light behaved differently than the speed of our flowing river in our picture of the Michelson-Morley experiment. Naively, according to the Galilean picture, if you had a train moving, say at 50 miles an hour along the track, and then it shines a light beam ahead of it, then according to the Galilean picture, the speed of light relative to the ground ought to be faster than the speed of light relative to the train, because there's the additional speed of the train, the 50 miles an hour, adding to the speed of the light beam. But if that's really how the world worked, then that would be bad news for the mathematical consistency of Maxwell's equations. And Einstein, in the first line of his 1905 paper that started the ball rolling on all of this special relativity, he name checks Maxwell. He says it is known that Maxwell's electrodynamics, and then goes on to explain the relevance of Maxwell's equations to the argument that he was developing. So in fact, in Einstein's picture, the speed of light is unchanged by the motion of the train, which again, if we switch from thinking about trains to thinking about electric and magnetic fields, similarly would mean that the structure of Maxwell's equations would be unchanged by the motion of the observer. But there was a big price to be paid for this. The price was that measurements of space and time were now relative to one's motion. And in the world of Galileo and Newton, that was completely off the table. Their way of thinking provided simple mathematical rules to transform how different observers would measure their position, would measure their velocity, but it was envisaged that all of this was unfolding against a static, unchanging backdrop that would be the same for all observers. Einstein turned that idea on its head. It called upon the idea of a unified space-time with, in fact, only measurements of a combination of the space interval and the time interval that would be seen as the same, as invariant by different observers. And indeed, in another of the papers that he published in 1905, would lead, or I think it was just early 1906 before it appeared in print, would lead to the equivalence of matter and energy, his famous E equals mc squared equation. So how does this come about? Well, I've tried to motivate it, again, recognizing that to do it properly would take way too long, but to motivate it just in terms of this idea of the structure of Maxwell's equations and preserving that for observers moving at different velocities. Let me try and do it a bit more quantitatively. Again, this is something I imagine most of you will have seen before, but it's the standard way as undergraduates where we get introduced to this idea of the relativity of space and time. And it's by doing a thought experiment, and the thought experiment involves a train. And it involves looking at a light beam that's bounced from the floor of the train carriage, reflected off the roof and back again, and to look at how that light beam would be observed by an observer on the platform and an observer on the moving train. So I'll be very brief with this because I imagine most of you have seen it before, but it will just remind us of how the argument works. So let's say the height of the train carriage is h, so 2h is going to be the speed of light times the time as measured in a frame that's moving with the carriage, so as measured by an observer inside the train carriage. But how would it look viewed from the platform? So we've got the train zooming by at velocity v, and from an observer standing on the platform, the light beam will appear to follow a path like this. It will be emitted from the floor, it will bounce off the mirror, and then it will come back again to the floor. But while that's happening, the train will have moved. So it means that the path is no longer vertical lines, the path is two sides of a triangle. So viewed from the platform, it's going to look like this. Now the base of this triangle is v times tp. So tp is the time as measured in the platform, v is the speed, the velocity of the train. And that's actually two right-angled triangles, so let's just look at one of them. And the base of one of those triangles then is going to be a half v times tp. And we had before that 2h was c times tc, because that was our height of the carriage. And if both observers measure the same speed of light, then the total distance as seen from the platform frame is c times tp. So that means that the length of the hypotenuse of a right-angled triangle is a half c times tp. So we've got a half c tc, a half v tp, and we just use Pythagoras' theorem to connect them together, and it gives us this expression between the time as measured on the carriage and the time as measured on the platform. They're not equal, and the relationship involves the factor known as the Lorentz factor that crops up all the time in relativity. This square root of 1 minus v squared over c squared. Again, as you all know, if v is very much smaller than c, then this effect will be negligible, and that's why in our everyday experience we don't see this sort of effect. If the speed of light, if the speed of a typical train, believe me, this is not the case in Scotland, I'm sure it's not in many other countries, if the speed of a typical train were rather closer to the speed of light, then we would see these phenomena in our everyday experience, but we don't. So to the observer on the platform, it appears that time is running more slowly on the moving train. So that's sort of a straightforward bit of algebra arrives at this result. But now we begin to ask, what does it mean? And in particular, a question that troubled me a lot when I was an undergraduate until it was properly explained. Why can't we think of the train as stationary as the platform is rushing past? Because after all, in that case, wouldn't it mean that to an observer on board the train, it would look as if the clock on the platform appears to be running slowly? So the answer to the question is that yes, that is indeed a correct way to interpret what's going on, and at first it feels weird. But that's because the time dilation effect that we've just seen needs to be viewed hand in hand with length contraction. So think of it like this, again, an illustration that many of you will be familiar with, I imagine, from undergraduate courses. We encounter this, for example, with cosmic rays. So cosmic rays that are incident on the top of the atmosphere, they can produce showers of muons. And those muons have a certain half-life. And if they were slow moving, they would never reach sea level because their half-life is only a very short time. a few microseconds. So in our frame, those muons are produced maybe 60 kilometers up. Their half-life is only 2.2 microseconds based on their typical speeds. Even if they're going pretty close to the speed of light, at first you would think, well, they're not going to reach the ground, but there's a subtlety here, a crucial subtlety, which is the muon lifetime to us appears to be greatly extended. That's the time dilation effect that we discussed. But we noted that it would be equally valid for the muons to think of them as stationary and the Earth is rushing towards them. In that case, it would be the time in our frame that's dilated. So how do we reconcile those two? In the muons frame, it's the case that their half-life is still only 2.2 microseconds, but from their point of view, it's the distance that they travel, which is less, which is contracted. So the time dilation and length contraction have to be looked at in the whole, in the round. And that's more or less how one gets round a number of potential paradoxes. There's a lot of scope for head scratching here when you start to ask questions that involve flipping your perspective from one frame to another. And indeed, very shortly, we're going to get on to some of the maths that we use to do exactly that. But it's easy when you're talking about the maths to forget that there's important physics that underpins all this. So the special relativity examples where the maths isn't particularly hard, the most you've ever got to do is use something like Pythagoras' theorem. That's not difficult. The really challenging thing is to keep track of which frame you're in and make sure that you're approaching the questions in a consistent and correct way. So again, I won't delay too long by going into these in detail, but you've maybe heard before of the pole in the barn paradox or the twins paradox. Very happy to discuss those later with people over coffee or a beer. And indeed, it'd be quite helpful to get some of your thoughts into how to best describe them. So the reason I put this in is that we've recently introduced into the high school curriculum in Scotland a little bit of special and general relativity. And believe me, the school teachers, never mind the pupils, are really freaking out over all this stuff. So I've been trying with other colleagues in the Scottish universities to supply some resources, put some things on YouTube and so on, to try to help them to explain to their pupils what's really going on. In fact, there's an excellent book I've been recommending, some of you might know this, by Chad Orzel, called How to Explain Relativity to Your Dog, which I can strongly recommend. So anyway, that's a bit of a diversion into special relativity, just rather shamelessly to give me the chance to say something about James Clerk Maxwell, but also to emphasise the importance of Maxwell's ideas and Maxwell's equations in giving us the origin of general relativity, and I suppose maybe most of all to emphasise that the speed of light has this really crucial role within the development of relativity. I know that's almost a statement of the obvious, but it will come back later on this morning when we look at where the wave equation for gravitational waves comes from and the importance that the speed of light plays in that. Okay, I should have said this before. When I refer to page numbers here, these are the pages in the long notes, the 96 pages or so version of the notes that will be made available later. So you can largely ignore that for the moment, but it's just so that you can, if you wish, later, looking at the longer version, which reads more like a textbook, you can connect the pages of that to the PowerPoint slides. So, we've talked about general relativity, we've talked about measurements of space and time being relative to an observer's motion, and we've talked in qualitative terms about how measurements of the separation, the interval between space-time events, involves measuring intervals of space and also intervals of time. So the way in special relativity that we codify all of that is in terms of what we call the metric. Again, I'm sure most, if not all of you, will have met this before in something like this form. So this allows us to calculate a quantity that we call the invariant interval, and that's because it really would be the same when you transform to another frame, the ds squared. But the dt squared, dx squared, dy squared, dz squared, those will generally change when you transform to another frame. But the metric tells us how to put them all together to get this interval, this measurement, this quantity that measures the separation of two events in space-time. It's about time we started talking about general relativity, so I'm just about to stop for a brief pause, but let's just spend a moment kind of motivating what will happen after the short break. One of the reasons why we need general relativity is special relativity describes the motion of observers moving at a constant velocity. In addition, special relativity falls short of a description that would be compatible with gravity. And as we're going to see in a few minutes after we briefly pause, there's a fundamental connection between gravity and acceleration that we express in terms of what's called the equivalence principles. But let's just think, before I stop, why Newtonian gravity, just on a kind of almost superficial level, why it's going to be a problem for a relativistic description. Well, one way to think about it, one way to begin thinking about it, is just to look at the form of the equation of Newtonian gravity. According to Newton, there's a gravitational force, a universal force between all massive bodies, and it depends on the separation of those two massive bodies. It's inversely proportional to the square of the separation between them. And you know, we've all heard the story that Newton was sleeping under the tree and the apple falls on his head and he comes up with this inspiration of the equation. But from an Einstein point of view, as we've just been looking at, there's a problem in defining what we mean by the distance between those massive bodies. That will be frame dependent. And that's not a good thing. Einstein wanted to think about gravity in a manner that didn't depend on the frame. He wanted to formulate the law in a manner that was frame independent, and there's a fundamental incompatibility of Newtonian gravity with that aspect of special relativity. The fact that special relativity tells us that the space-time interval is invariant, but the interval in space, the separation of the two massive bodies, is not invariant. Also, in Newtonian gravity, I guess it's implied, I'm not sure, don't know enough about Newton and exactly his thinking on the matter, maybe some others in the room do, but I think it's implied that the force of gravity was instantaneous. That also is problematic within special relativity because intervals of time will be frame dependent. So what we need is some way of thinking about gravity that is compatible with what Einstein had learned about the nature of space and time by developing special relativity. Or to put it another way, if this force instantaneously reaches out from one massive body to another, then one could ask the question within the framework of Einstein's emerging relativity theory, how does the moon know it's supposed to orbit the Earth? How does gravity act at a distance across space? So that takes us all the way back to the neat phrase of John Wheeler, where matter tells space-time how to curve and space-time tells matter how to move. Newtonian gravity gives us a piece of mathematics. It talks about the force between the massive bodies, but how does the moon know that it's experiencing that force from the Earth? How does it act at a distance across space? So what we need is a way of thinking about gravity that avoids this notion of Newton's force, partly because action at a distance is a problem. Just philosophically, how does the force get from one place to another? And secondly, even defining what we mean by distance is a problem anyway, if you want to look at things from the point of view of different reference frames. So what we're going to do is we're going to rethink the idea of gravity via the principles of equivalence. And we'll pick that up in just, say, 5 minutes' time. Give everyone just a little minute to think. Okay, thank you. Associated with the F equals ma, the equation of Newton that relates applied force to acceleration, essentially the amount of force that one needs to apply to this bottle to make it accelerate across the bench. That will depend on the mass of the bottle. The more massive, then the more force I would need to apply in order to push it across the bench. The gravitational mass tells us something about the gravitational force between the earth and the bottle when I let it go. But of course, when I let it go, it falls, it accelerates. So our everyday experience makes us perhaps just take for granted that these two masses should be the same. The inertial mass that appears in this equation, determining acceleration, and the gravitational mass that appears in this equation, determining the gravitational force. But there's nothing that says they have to be the same. And Einstein's starting point for what we call the weak equivalence principle was to say that they are the same, that they're identical. Gravity and acceleration are equivalent. And that gets us a long way in thinking about how gravity might fit in to the relativistic picture. In particular, it says then that an object that's freely falling in a uniform gravitational field, it inhabits an inertial frame in which the gravitational forces have effectively disappeared. This basically is why astronauts on board the space station, or I think this picture is older, it's from the space shuttle era, it's why they would be weightless. Because the shuttle is inhabiting an inertial frame in which the gravitational forces have effectively disappeared. But it's only what we call a local inertial frame. It's only local over the region for which you can view the gravitational field as uniform. We'll come back to that point in a minute when we start to do some simple calculations to guide us towards what's really going on. What we can say though is that locally, in a local inertial frame, we can go further. The weak equivalence principle says that gravity and acceleration are equivalent, but we can postulate what is referred to as the strong equivalence principle that says that actually all laws of physics reduce to their special relativity form, meaning the form they would have in a reference frame that's inertial, where the observer is not accelerating, apart from gravity, which simply disappears. So, in a local inertial frame, that's what you would inhabit if you're, for example, on board the space station orbiting the Earth. Then all laws of physics should reduce to their special relativity form, apart from gravity, which effectively disappears, which means that you're weightless. So these equivalence principles actually already, even before we introduce some of the heavy-duty mathematics, the tensors and the metrics and all of that will come later, already just the physical idea of the equivalence principles can guide us towards some very important predictions of general relativity that begin to differ from the predictions of Newtonian gravity. The one that's probably easiest to illustrate, and one that again many of you have probably heard before, is the fact that light is deflected in a gravitational field. So let's see how we can arrive at that conclusion just by thinking about the physical idea of the equivalence principle. So what we've got is we've got a lift or an elevator. To depending on your cultural background, you might not know that the word lift. I was on sabbatical in the US more than 10 years ago, and they asked me to do a course on relativity. And I was a little worried that the students in the university I was visiting might not have done the kind of maths that they would need to get very much out of a course in relativity. But actually, they were fine with all of that. The thing they were most troubled by was A, my Scottish accent, and B, using words like lift and torch instead of elevator and flashlight. So once we had a common language, and once they'd got the hang of my accent, then they handled the mathematics just fine. So hopefully you will as well. So whether you call them lifts or elevators in your part of the world, what we've got is our little figure here, person A, who's inside the lift as light is travelling horizontally through a little window at position X. And then the lift begins to fall. The lift cable is snapped and it begins to free fall downwards. So at that moment, when the lift begins to fall, person B is watching that happen. And person B is standing on a platform experiencing the gravitational field of the Earth. A uniform gravitational field, we'll assume, for our purposes, of gravitational acceleration g. Again, that's meaningful because the equivalence principle says that the gravitational force and the inertial force are equivalent to each other. So we can take the m times the mass of the Earth divided by r squared and relate that to a quantity small g, which is the gravitational acceleration. So observer A is in a local inertial frame when the lift cable snaps and it begins to fall. So observer A will see the light beam travel horizontally across the lift because the equivalence principles say that what the light beam does should agree with special relativity because it's a locally inertial frame. And according to special relativity, light beams should just go in straight lines. So that means observer A sees the light beam emerge at point Y. But during the time it's taken the light beam to go from X to Y, the lift has fallen. So as seen from the point of view of observer B, point Y is actually a little below the level of point X. So how do we reconcile these two observations? In order that observer B's interpretation of what the light beam is doing is consistent with what observer A says, basically the light must follow a curved path as seen by observer B. And observer B interprets that curved path as being caused by the gravitational field. So the equivalence principles leads us towards the observation that light should follow a curved path in a gravitational field. Now later on, when we briefly look at how we describe this in terms of a metric, what we call the Schwarzschild metric, then we'll see a bit more quantitatively how that comes about. But the basic idea is there as soon as you buy into the notion of the equivalence principles and the fact that both observers in their two frames have to reconcile what they see with the laws of physics. A similar setup can lead you to the observation, the sort of prediction, if you like, that gravity should cause light to be redshifted. The gravitational field should cause light to be redshifted. So what we would do there is we would emit a light beam from the bottom of the lift, upwards vertically, and then the lift begins to fall. And think about what the two observers would perceive. So you can maybe try and construct that one for yourself. So we've got the equivalence principles telling us already that there are some differences between the predictions of Newtonian gravity and Newtonian gravity extended now to the relativistic setting, what Einstein would later turn into his full-blown general relativity theory. Another key step along the way, having established the equivalence of gravity and acceleration, is to think of both gravity and acceleration in terms of curvature. And again, we'll do that properly shortly, albeit very quickly, but we will give you a sense of where the proper mathematical description of space-time curvature fits into the picture. But let's first of all try and do it not so much in a hand-wavy way, but in a way that doesn't get bogged down in too much maths, but gives you some pictures to hook your ideas onto. In fact, let's go back to our idea of the stretched rubber sheet. Space-time tells matter how to move, matter tells space-time how to curve. Remember the rubber sheet with the Earth in it? We think of that as a picture of how the mass of the Earth distorts the space-time around the Earth. So, if we want to think of gravity and acceleration in the context of the geometry of space-time, what we're really saying is that gravity manifests itself in an effect on the natural paths that objects will follow in space-time. What are those natural paths? Well, we call them geodesics. They're the equivalent of straight lines. Straight lines is the natural path that a body will follow on a flat surface. If you have a curved surface, that's what the whole space-time curvature stretched rubber sheet picture is trying to convey. The curved surface, if I roll a marble, then it will follow a curved path because of the curvature of the surface. So the natural path that the body will follow is no longer a straight line, it's curved. So whereas Newton's first law says that unless acted upon by non-gravitational force, a particle will follow a straight line, now in a universe where space-time can be curved, what we say is, unless acted upon by non-gravitational force, a particle will follow a geodesic. So geodesics are not necessarily straight lines, but they're still the natural paths that bodies will follow unless they're acted upon by some other force. So how can we use geodesics to tell whether or not our space-time is curved? What we do is we look at neighbouring geodesics and see how their separation changes. So here's a two-dimensional analogy, but it captures the essential feature of what we need. So here are three surfaces, just spatial surfaces, but surfaces with different curvatures. There's a flat piece of paper, or cardboard. There's a surface with positive curvature, like the surface of a tennis ball or a baseball. And there's a surface with negative curvature, like the surface of a saddle or, a Pringle. Think of them. So in those three surfaces, if I take two neighbouring geodesics, which are initially parallel, just in the common sense definition of parallel, pointing in the same local direction, we're going to delve into exactly what that means for curved spacetimes in a few minutes and start to think of, can we trust what we mean by the notion of direction in curved spacetimes? But for the moment, let's just go with our kind of common sense definition. So these two little ants start off in a parallel path. If the surface has zero curvature, then the two paths remain parallel. They remain the same distance apart. If the surface has positive curvature, then the paths get closer together. They converge. The geodesics accelerate towards each other. If the surface has negative curvature, then the geodesics accelerate away from each other. They move apart. So that gives us, before we get bogged down in all the maths that describes it properly, it gives us a physical picture of what we mean by a gravitational field acting on a massive body. If you've got a non-uniform gravitational field, then what it will cause is the geodesics to accelerate. There'll be a deviation, a change in the separation of neighbouring geodesics. And that change in time causes them to accelerate towards each other for a positive curvature space or away from each other for a negative curvature space. In other words, that non-zero acceleration, whether positive or negative, is an indication of non-zero curvature. So what that's given us, with the detailed maths to follow shortly, is a way of thinking physically about how to connect the notion of gravity and acceleration to the curvature of space-time. What we've got to do is work out what our natural geodesic paths are and then see whether they converge or diverge. And that gives us insight into the nature of the gravitational field. So how big an effect might we expect all of this to be? After all, we said before the break that a lot of the special relativity effects run contrary to common sense because we're not accustomed to travelling close to the speed of light. Similarly, we don't usually think of space-time curvature. Maybe that's also because we're not accustomed to environments where the space-time curvature is very large. That's kind of what you might suspect as part of the reason why it took all those decades and centuries from the work of Newton before Einstein comes along. Well, let's see if that checks out. Again, thinking about it in a more simple mathematical way might give us some physical insight that will help us when we start introducing all the heavy-duty maths. So suppose we've got two parachutists. Okay, I've not really drawn this to scale. I wouldn't like to begin my parachute jump from that far above the earth. I saw that Austrian chap jumping off the, 100,000 feet he jumped from. That was way scary enough. This looks as if it's even further. So it's not drawn to scale, but what I'm emphasizing by drawing it this way is that even in a Newton description, where we're just thinking about gravitational forces, nothing more complicated than that, we can already see that there's a non-uniform gravitational field, because the direction of the force from this parachutist towards the centre of the Earth is not the same as the direction of the force for that parachutist. Now actually the same would apply even on board the International Space Station. A few slides ago I talked about a local inertial frame, but I didn't specify how local was local. And it really depends on how well you can measure the direction of the gravitational field. So I've drawn this in such a way that it's obvious that the gravitational field is pointing in a different direction, the gravitational acceleration vector, as Newton would describe it. But even if we were considering something much, much smaller, if you could measure the direction of that gravitational acceleration accurately enough, then you would still realize that you're not in an inertial frame. But anyway, let's see where this takes us. We've got our two parachutists, and they begin to free fall towards the Earth long before they open their parachute. And their separation, I've denoted by this Greek letter xi, and then their initial separation is xi0, and then after some time t, they've got closer together because they're falling towards the centre of the Earth. And they're falling not in a parallel direction, but in a converging directions. So just by using some simple geometry, flat space-time or flat space, by using similar triangles, we can obtain this differential equation for xi, the second time derivative of xi. So that's using Newtonian gravity and then using similar triangles. And the reason we do this is because what we can then do is we can turn this into a differential equation for xi, changing our time variable from t to ct, and that's just so that we collect together some constants that begin to look quite interesting. Our equation for how xi evolves with respect to the variable c times t that differential equation involves psi, but it also involves this combination of constants. So r here is the radius of the Earth. Now again, I've not drawn this to scale to exaggerate the effect, but we're assuming here that small r is, going the wrong way, that small r is not so different from big R. In other words, the parachutists aren't beginning from too high above the Earth. What we get then is that g times m divided by r cubed times c squared times psi, that's on the right hand side of our differential equation. And the thing is, at the Earth's surface, this number, which has got units of inverse area, this number is really small. But what does this number signify? It's not maybe obvious from just looking at the equation what that number means. So to try to see, sort of approach it a slightly different way to see what that number might represent, let's introduce another similar differential equation. This time not with falling parachutists, but just on the surface of a sphere. So hopefully this analogy will help us to interpret what that last term actually meant, the gm over r cubed c squared, which, when you work out what it is, for the mass and the radius of the Earth, gives us this very, very small number. So what we've got now is 2 points on the surface of a sphere, and if they're along the equator, let's suppose that they're separated by psi 0, and then let's ask what happens when they both move up a circle of longitude towards the pole. As they move along that arc, sorry, I'll save that slide just for a moment. As they move along that arc, the points get closer together. And again, we can crank through some simple algebra to try and give us a way of saying, expressing, how psi changes as a function of s, the arc length. And that differential equation involves 1 over a squared, where a is the radius of the sphere. Now if we compare that with the previous slide, so again, let's just try and jump between those two. There's a differential equation involving minus this term times psi. And then here's a differential equation involving the second time derivative of psi minus this term times psi. So they've got the same mathematical form. We can see in this case that the role played by this term is 1 over the radius of the sphere squared. So that would suggest that the quantity we had here, gm over r cubed c squared, but again we can think of that as 1 over the radius squared of something. Well, it's not the radius of the Earth. You can think of it instead as the radius of curvature of space-time at the Earth's surface. And that's a much, much bigger number. So what we've got is a massive object which happens to be spherical, so we can attach a radius to the Earth itself. But again, the Earth is sitting in our stretched rubber sheet, and that stretched rubber sheet has got a certain curvature, which by these simple analogies, we seem to have arrived at a number which is very, very much bigger than the radius of the Earth. Which kind of suggests that what we've got is a compact sphere, the Earth, sitting in a little dimple in space-time, but that space-time dimple has got a much bigger radius. In other words, the mass of the Earth hardly disturbs the curvature of its local space-time at all. So we haven't yet introduced any complicated mathematics to try and capture that more rigorously. I'm just about to. But what I've sought to do so far is to give us a feel for why the effects of the curvature of space-time and the convergence or divergence of the geodesics, which are the signatures of a non-gravitational field, those are all pretty weak in the vicinity of the Earth. But now it's time to try and describe all that in a more rigorous mathematical way.
Excuse me?
Yeah.
So you said that gives us hint that the Earth doesn't influence too much the space-time curvature around it. But like that whole radius is just created because the Earth is sitting there, right? So like in what sense do you mean it doesn't influence much?
Yeah. In a sense, if you do the same calculation for a neutron star, then what you find is that the radius of curvature of space-time, expressed by this combination of constants, is much closer to the actual physical radius of the neutron star itself. And for a white dwarf, it's closer but not so dramatic as for the neutron star. So I appreciate I'm being a little bit imprecise. I'm just trying to guide us towards an understanding of why, there is gravity on the Earth, but it doesn't really affect the space-time curvature dramatically, not so dramatically as a white dwarf or a neutron star. It's partly to do with the way the equations connect together. It's also to do with something which I wasn't really planning to cover because I wouldn't get far enough into gravitational waves to cover this, but let me mention it now because it relates very much to your question. One of the ways that we can think of why gravitational waves are so hard to detect is that space-time is incredibly stiff. You need to accelerate mass a lot in order to produce any kind of curvature and change in the curvature of space-time. So that links to this in the sense that, like I just said, if we think about it just in terms of the stretched rubber sheet, we've got the Earth, which, has got a certain physical radius of curvature, but when you drop that down onto the rubber sheet hardly bends at all because it's very, very stiff. Just like if I dropped a cannonball onto this bench, I won't do it. I think our hosts in St Andrews wouldn't be very happy, but the bench wouldn't bend very much. If I dropped the cannonball onto a trampoline, it would bend a lot. Okay? So that's all I'm really getting at. So you can try doing the calculation yourself for, as I said, a typical white dwarf, which would have the mass of the Sun, but the radius of the Earth. And you'll see that, of course, that gives you a space-time curvature, a radius of space-time curvature, which is much smaller and much closer to the actual physical curvature of the white dwarf. Okay, so we've held back the introduction of the more detailed mass for long enough. So let's spend a little time now talking about the basics of tensors. So what we need is a mathematical toolbox that's capable of describing the curvature of space-time in a completely rigorous way so that we can describe the laws of physics within curved space-times. So what kind of mathematics would fit the bill? Well, again, forgive me if I get some of the historical details wrong, maybe others in the room know them better, but many of you have probably heard the stories about Einstein skipping a lot of lectures that he should have attended when he was studying in his undergraduate degree. But fortunately, his great friend Marcel Grossmann did go along to those lectures and was later able to help Einstein put the pieces together. What Einstein needed to describe the physics of general relativity was the mathematics of curved spaces that was had been developed a few decades before in a completely abstract context, but it fitted Einstein's needs really well. So the mathematics of those curved spaces involve things that we call Riemannian manifolds. So what's a Riemannian manifold? It's something that's a sort of a structure, a mathematical structure that's continuous. That means it's smooth. It's differentiable. Well, that's good because when you're developing the laws of physics, they usually involve changes. They involve changes in time. They involve changes in space. So you want to be able to define quantities which are the derivatives of other quantities. So Riemannian manifolds can do that. The most crucial aspect of it is that a Riemannian manifold is a continuous differentiable space which is locally flat. So that means that globally it could have some significant non-zero curvature, but if you home in on a small piece, a sufficiently small piece of that surface, then it will be describable using the geometry of a flat surface. And we also need to be able to define a distance on that surface using a function that we call the metric. Now this was ideal because the mathematical properties of a Riemannian manifold, they match the physical assumptions of the strong equivalence principle. Remember, we discussed those just a few minutes ago. The strong equivalence principle says that in a local inertial frame, everything will agree. Special relativity plays out on a flat space-time. Using the metric that we flashed up briefly in the slide, we called it the Minkowski metric of flat space-time. So Riemannian manifolds have exactly the property that one would wish if you want the behavior of physical laws to reduce to what special relativity says when you consider a local region of space-time. So that's what we're going to use. So here's an example of a Riemannian manifold. My attempt to crudely represent it as a two-dimensional projection. Just a curved surface, but a curved surface which is locally flat. So what we need is a way to describe geometrical objects on that curved manifold, that curved surface. And we need to be able to describe them in a manner that allows us to add them together, multiply them, do all those operations, but also do things like differentiate, so that we can use them to describe physical laws in that curved manifold. So I've got a question for you. Do these two vectors, positioned at x and y, do they look the same? How many people think they look the same? How many people think they don't look the same? And how many people aren't sure? Well, in a sense, the aren't sure answer is kind of the right one. I've put them on there in a way that makes them look the same, but I suppose maybe let's ask another question. If you thought they looked the same, then why did you think that? Can you think what process you went through to try to decide if this vector was the same as that vector? Anyone like to tell me? Yeah. Exactly. So that's what you do. You instinctively imagine taking this vector and translating it across to that one and seeing if the two arrows match. Now that works just fine in flat space. In fact, it doesn't even always work in flat space, but in the simple situation where you have what we call Cartesian basis vectors, what we learn about at high school, ijk or ex, ey, ez, orthogonal at right angles to each other, and the same everywhere. If that's the basis vectors you use to describe your space, then the process of translating this vector to this one is trivial. And it's kind of what we just do in our head when we try to answer the question, is one vector the same as another? But we need something that will work even for curved spaces. So how would we describe these vectors? So one way to do it is notation like this, and you're going to see a lot of this over the 2 weeks, so let's introduce you to some of its features if you haven't met it before. Firstly, you can see an alpha as a superscript and also as a subscript. So that denotes a sum. It's usually referred to as the Einstein summation convention, and it's just a shorthand to avoid us needing to write those big capital sigmas whenever we want to denote a sum. So what this says is that the vector delta x is a sum of components. That's how you learn about vectors. You learn that vectors involve components sort of parallel to the coordinate axes. So you've got a component times a basis vector in the x direction plus another component times the basis vector in the y direction. And then you can extend that to 3 or more dimensions. So the components here are denoted by delta x alpha, where alpha would be 1, 2, 3 if it was x, y, and z. And then the basis vector. So in general, components of vector are going to be different to x and y, even if the vector is the same at both points, because the basis vectors might change. Okay, so let's think of a everyday situation that you've probably encountered already where that's true. Think of vectors on a sphere. So what we've got here is a vector at x. Well, in fact, I've just drawn the basis vectors, but we could add an arrow to that slide, and then you could define the components of that arrow in terms of the basis vectors. You could decompose the vector into the basis vectors. But I've written these basis vectors as e theta and e phi. And this is very common. What we often do is define the basis vectors in terms of what we call tangent planes. So they're defined in terms of the direction in which one coordinate is changing. So in other words, e theta is in the direction of theta changing but at fixed value of phi, and e phi is in the direction of phi changing but at fixed value of theta. Now you could define other basis vectors, but that's a perfectly reasonable set of basis vectors to use. The trouble is, when we move to point y, the basis vectors e theta and e phi no longer point in the same direction. So because the basis vectors have changed, the components would also change if we were talking about the same vector. So my innocuous question about whether these two vectors are the same, yes, they could well be the same, but the components we would use to describe them would necessarily have to change if the basis vectors were changing from one place to another. We need to be able to handle changing basis vectors and their components on surfaces of arbitrary curvature. And that's where all the messy mathematics comes in. So in fact, what we can think of doing is transforming from one coordinate system to another, just like we did right at the beginning. We thought about, the red car and the blue car, transforming reference frames from one observer's point of view to another. Well, those reference frames we can just define in terms of the coordinates that give us the positions of events. And that means we've got a different coordinate system for one frame compared with another. We need a way to transform from one coordinate system to another. And that transformation has to work even if the coordinates are curved, even if the space-time is curved, so that the natural coordinate system, like for example this one, just using the tangents, well, those tangents, just like they do even on the sphere, the basis vectors will change. So we need to be able to capture all of that. So a way to arrive at the relationships we need to tell us how to change things like vectors from one coordinate system to another is to ask the very general question, how does a vector transform when we change coordinate system? And in fact, we can use this in a way as a definition of what a vector is. A vector is a thing that transforms like this, so that the components of the vector in one coordinate system get turned into the components of the vector in the new coordinate system according to a particular mathematical relationship, a linear relationship. Linear relationships are great. They simplify the physics enormously if we have linear relations telling us how to change from one system to another. And we can regard that as the defining characteristic of a vector. But why stop there? Why stop at essentially what we have here is one set of functions which are like the coefficients of the coefficients. So before we were thinking of these, the components of the vector. Now, if you're thinking about the transformation law, what you're really interested in is the other terms, is these ones, these partial derivatives, because they're telling you how the components change from one coordinate system to another. As I said, why stop at the form we have for a vector? We can introduce more general geometrical objects, these things that we call tensors, and vectors are just a special case of them. But of course the notation very quickly gets really messy. So I'm going to try and use this tensor description as little as possible, and I think the lecturers that follow will probably do the same, but we can't avoid it because it's crucial to help us understand in detail some of the maths of gravitational waves, but we're not going to work with general expressions as messy as this. Essentially, the way it works is that you can think of a tensor as a geometrical object with a certain number of slots, and those slots correspond to certain basic forms out of certain building blocks of the tensor. So the building blocks can either be vectors, which we sort of have a vague sense of from primary school, well, maybe not primary school, certainly secondary school. And they can also be other objects that we call one-forms, or sometimes referred to in older literature as covariant vectors. So what you've met at high school as vectors, we can call contravariant vectors. This all goes back to a few slides. Notice that I've put an upper index on the coefficients. You might not have met that before, where we normally think of upper indices as just being when you're squaring something or cubing something. That's not what it's representing. It's just representing an element. You know, could be delta x1, delta x2, but normally we put those as lower indices. But in certain circumstances, when you're dealing with curved spacetimes, it does matter whether it's an upper or a lower index. There are ways in which you can change from one to the other, but they require a rigorous application of certain rules that tell you how to do that. Again, it's not something we want to get too bogged down in, but that's why in our very general expression for a tensor, we've got both upper and lower indices, because the most general form of tensor we can have is one in which it's sort of decomposable. It's constructed out of building blocks which are both vectors and one-forms. And that is why you have the mixture of upper and lower indices.
Excuse me.
Yeah.
I'm sorry if you just said this, but could you give like a one-sentence summary of the difference between a vector and a one-form?
I'm gonna. I'll come to that, but let me do it now, and then we'll do it again in a slightly different way. I anticipated that someone might well ask that question. A good example is the gradient, right? Now you think of the gradient as a vector. If you've encountered that, say, in a course in electromagnetism, you can talk about the gradient of an electric potential, or indeed the gradient of the gravitational potential is another concept that one meets. So normally we think of that as a vector, but it actually isn't. It's a one-form. Now the reason that we don't get hung up on the difference is that if you're dealing in flat space, then vectors and one-forms are trivially related to each other. Whereas if you're dealing in curved space, you've got to be a little bit more careful about changing the components of a vector into the equivalent one-form expression. Now, the key to doing that involves what we call the metric, and that's what I'm coming to in a couple of slides' time. So again, physically think of the gradient as something which, despite you maybe thinking of it as a vector, it actually isn't. Now again, I don't have this slide, so this might be worth me just drawing on the board, and then we'll come back to it. Are there pens around? I'm missing them, there they are.
And that's just because it transforms slightly differently than a vector?
It does, yeah, exactly. So let me show you that. So there's the transformation law for a vector, that the components of the vector will follow this relationship, whereas the transformation law for the components of a one form look like this. So notice I've changed upper to lower indices. You think, well, what's the big deal? That's just a bit of maths. But again, the picture to think of is if you had something like an ordnance survey map. Okay, so where the contours of the ordnance survey map are close together, that tells you that you're going steeply uphill or downhill. So, I mean, if you're climbing a mountain, there aren't so many high ones close to St Andrews, but again, in the trip next weekend, you might go in some fairly rugged terrain, and there'll be certain routes that will be more perilous than others because they'll involve a steeper descent or steeper ascent. The way you would recognise that in an ordnance survey map is that the contours would get very, very close together. So, there's a way to interpret these contours in terms of one forms. I mean, that's really what the gradient is. But as I said before, normally we just think of the gradient as a vector. So what's the big deal? So I'll come back to this diagram in just a minute when I get on to talking about metrics, and I'll take the specific example of the gradient operator and hopefully demonstrate how we can turn that one form into a vector using the metric. Okay, so I'll come back to that. So in general, we're not going to see anything as horrible as this, but we are going to work with things like, as I've just been saying, the metric tensor. So the metric tensor is shown here as a 0, 2 tensor. That means it's got two lower indices, and this is the transformation law. So in other words, if you had the components of the metric in one frame and you wanted to transform them to another frame, this is the way you would do it. You would use an expression like this. So for special relativity, we had an expression ds squared equals minus c squared dt squared plus dx squared dy squared dz squared. We called that the Minkowski metric. Many of you have probably met that before. But we can now generalize that metric to something like this. Remember the Einstein summation convention? There's a mu on the bottom and a mu on the top, so that indicates summing. Now it's actually over 4 indices, denoting t, x, y, and z. And then we've got two nus, a nu on the bottom and a nu on the top, so we sum over those as well. Now fortunately, quite a lot of them are 0 in the Minkowski case. So in fact, this general expression, this could be 16 terms, but only 4 of them are non-zero for the Minkowski metric. And indeed the components, the g mu nus, even the non-zero components, are constant. They're minus c squared 1, 1, 1. But for a general curve space-time, these could actually be functions. These can be functions of space and or time. Now, there's a certain symmetry condition which says that instead of having 16, you've actually only got 10 because the G12 component should be the same as the G21 component. Essentially, think of that as saying that since the metric tells you the distance between 2 points in space-time, it shouldn't matter whether you measure the distance from here to here or from here to here. So a consequence of that symmetry means that the metric winds up being symmetric in that way. So I want to save covariant differentiation for later, but let me just see if I can come back to that question. Maybe I didn't have it after all. Right, so back to gradients. What I want to do is just to spend 2 minutes before we stop for coffee talking about how to convert one forms to vectors. All of this is in the longer version of the notes, okay? But since you asked what's a very pertinent question, let me say that say we've got the gradient, right? So the gradient operator, we might sort of say represent it as like that, nabla phi. You've probably seen that notation in previous courses. What I'm saying is that you've traditionally thought of that as just like a vector. It's probably been presented in that manner in, say, electromagnetic courses. But in actual fact, it's really a one form. So that means it transforms this way instead of this way. Now, how do we link the two? Well, the point is, if you've got vector components, A mu, and you want to turn them into the equivalent one-form components, what we do is we say that A mu is equal to G alpha mu A alpha. So this is the summation convention again. So what you do is you take the metric and you sum over the metric components, and that basically turns the A alpha, the vector version components, into one-form components. Now, my point is, how it relates to the slide we've got there, is that if you're talking about flat space, or even flat space-time, the metric is so simple that when you do this operation, you're generally just multiplying one. So, yeah, so say if we take the Minkowski metric, so let's say we wanted to consider the x component. So AX would be G Tx AT plus GXX AX plus and so on. But only this one would be non-zero, and in fact GXX is 1. So the two are trivially related. But if you're talking about a general curved space-time, then they won't be so trivially related. So you have to mathematically make a distinction between one forms and vectors. Well, that's all very well, but physically what's the difference? Well, that's back to this. The one form is actually more a statement about how close together the contours are. So if I take a one form and I operate on it with a vector, what I should get back is a scalar. Or if I take a vector and operate on it with a one form, what I should get back is a scalar. So how would that work for the gradient? Well, let's take an honest to goodness vector, which is like an arrow. Okay? If I take, say, this point, and I operate on the one form that's defined by these contour lines, and I say operate it on that, by that vector, that arrow, the scalar that's associated with that operation is basically the number of contours that the arrow crosses. Okay? Now, if the one form has got a greater magnitude, then it means that the contours are closer together. So a vector of a given length will cross more contours when it operates on that one form. If the one form has got a lower magnitude, then it means the contours are more spaced out. It means it's a gentler gradient. Therefore, when you operate on it with a particular vector, the scalar you get, which is the number of contours you cross, will be a smaller number. Okay? So does that help a bit? Just give some insight into how one forms, on the one hand, in simple situations are trivially related to vectors, so you can more or less just regard them as the same thing. But as soon as you're into curved spaces in general, they're not the same, but they're things that when you operate on them with vectors, you get scalars, and this is an example of how that would work. Okay? Introduction to GR and gravitational waves. So we are very firmly now talking in GR terms. We haven't got onto gravitational waves yet, but we will before lunchtime. And the next piece of our mathematical toolbox that we need to try to understand is how to do differentiation on curved space-time. So the laws of physics usually involve derivatives of quantities, either in space or in time. So if our goal is to find a way to formulate the laws of physics in curved spacetimes, then we need to know how to do differentiation in curved spacetimes. And that might seem trivial, but usually what differentiation involves is the limit of a process when you compare a quantity in neighbouring locations and you ask what happens when the separation tends to 0. So if you look at our picture here, suppose again we think in terms of vectors. Well, this relates to that question I asked during the second session. We had the two vectors at x and y, and I asked if they looked the same, and we agreed that what we instinctively do to answer that question is we imagine translating one vector over to the other position and see whether they match, see whether the components match. Well, we went on to see that that's difficult in curved spaces because the basis vectors will change, and that means that the components will change. So we need to have a way to keep track of how the components change when we move from one location to another. So specifically, if we're doing differentiation, then this problem is a very real one, because if we want to take the derivative of some vector field, and it is described in terms of components AI, then that will basically involve comparing those components at x with the components at a neighbouring point x plus dx. But since the basis vectors can in principle change between x and x plus dx, what we really want to do instead is to find a way to translate AI, keeping track of how the basis vectors change, so that we can define the equivalent of AI actually at the position x plus dx. So I've called that dAI here. So we need a procedure for transporting the components of A to a neighbouring location. So we call that parallel transport, and it's the key to doing differentiation on curved spacetimes. Now, more generally, there are other ways this can be done. I'm just looking at a subset of the necessary maths because, again, there isn't time to go into other ways of doing it. There are things called Lie derivatives, for example, which are used a lot in particle physics, in quantum field theory. But I'm just looking at covariant differentiation, which is the standard approach used for general relativity. And again, I've tried to keep the maths to a minimum and focus instead on pictures and focus on diagrams to try and illustrate what's going on. So we say that a vector field is parallel transported when it maintains a constant angle with the tangent vector to the curve. So the tangent vector, that's I'm just touching, as the name suggests, the curve at point tau, and then we parallel transport that along to tau dash. The angle between this particular vector and the tangent vector it happens to be a right angle, just because it's a nice way to illustrate it. And yes, when it's parallel transported to here, that's still a right angle. So, as you might expect, there's lots of algebra associated with this, but don't get freaked out by the algebra. In a way that doesn't matter so much. Let's just try and deconstruct what the algebra is actually doing. So when you parallel transport AI over to here, dAI, so that you can then subtract the components at the same place, and therefore you know the basis vectors are the same, then what that does is it involves basically modifying the components at x by a small amount. Well, hopefully small, if you're not moving very far in the curved space-time. So these modifications to the components, delta AI, we can write them in terms of a different set of coefficients that are usually referred to as Christoffel symbols or connection symbols. And you can think of them as telling you how to connect one point in the curved space-time to another point. Well, what does that actually mean? It means how to connect the components of vectors or tensors to the components at some other location. And in particular, specifically, what the Christoffel symbols do is they tell us how to map the basis vectors at one place to the basis vectors at another location. So it tells us how the basis vectors change as you move through the space-time. So if we're talking about curved space, then those basis vectors may well change. Remember the example of the surface of the sphere, and the basis vectors were just the standard ones, e theta and e phi, but we showed that when we went from one position to another, the direction of e theta and e phi was changing. So this expression would tell us how they change, and we could relate those changes to these Christoffel symbols. So what all of this means practically is that we can define a covariant derivative, which is a quantity that transforms like a tensor. It has the appropriate transformation properties so that we can formulate the laws of physics in a way that will look the same in terms of the structure of the equations in any coordinate system. Ordinary partial derivatives don't do that. So the covariant differentiation of a vector, the components of a vector, is not the same as the partial derivatives of those vector components. We have this extra piece to add on, which is expressed in terms of these Christoffel symbols. And again, think of the Christoffel symbols as telling you how the basis vectors change from one place to another, which is what you need to know so that you can correctly adjust the components of the vector field when you move from one place to another. So the idea of covariant differentiation and parallel transport provides us with a way now to think rigorously what we mean by a geodesic. So we talked about geodesics much less rigorously, just in terms of the natural path which a particle will follow as it moves through a curved space, the analogy of a straight line on a flat surface. Well, what do I mean by natural path? How could we define that more rigorously? Well, we can do it like this. A geodesic is a curve along which the tangent vector to the curve is parallel transported. So if you parallel transport a tangent vector along a geodesic, then it remains a tangent vector. So again, it may be that some of the subsequent lectures will draw upon that definition. I'm not sure actually, but then it's there for you. And the longer version of these notes goes into a little more detail on where these results come from. We're almost done now in terms of sort of filling our mathematical toolbox. We've talked about the notion of what a tensor is, albeit very briefly, and we've talked about metrics. We've talked a little bit about one-forms and vectors and how you can operate on one with the other, and what you get is a scalar, and we used this example of the gradient as a way to think of that. We've also now introduced the idea of how to differentiate vectors in one-forms and tensors. So now we're ready really to start to try to derive Einstein's equations. And again, we're going to do that very swiftly, but there's much more detail in the longer version of the notes. If you want to see all of that detail, then you can download them once we post them on the SUSSP website. So remember, we started with the qualitative phrase due to John Wheeler: space-time tells matter how to move, and matter tells space-time how to curve. And you could say the whole purpose of these lectures is to turn that qualitative phrase into something involving equations. So we're almost there. We now need an equation for how the space-time curvature is described, and then in a few minutes we'll get an equation for how the matter and energy is described, and we'll put those two together, and that will be Einstein's equations. So firstly, there's the space-time curvature, and this is described by something that we call the Riemann-Christoffel tensor. So if you think all the way back to the first session, remember I had the example of the sphere, and we worked out what the radius of curvature of the sphere was and how that related to a differential equation for how lines of constant longitude would converge as you approach the North Pole of the sphere. You start off in the equator, and then the lines of constant longitude will converge together. And the differential equation for that was related to the curvature of the sphere. Now, spheres are maximally symmetric. They've got all sorts of beautiful symmetries. So that means that the expression for the curvature was just a single number. It was the radius. That's the only number you need to specify the surface of a sphere. But if you've got a general curved space-time, then you maybe need lots of numbers to describe the curvature, because the curvature might be different in different directions, for example. And it's certainly going to vary from one place to another. So that's why we need a tensor. And in fact, it's a rather complicated tensor. It's a tensor with 4 indices. And that means in principle it could have as many as 256 different components. It's a lot more complicated than just a single number, which is the radius of the sphere. But the idea is the same. It's a number which captures something about the local curvature of space-time, and therefore we might expect that if you measure this Riemann-Christoffel tensor for a flat space-time, you're going to get 0. Well, let's see how that might come about. Well, in fact, I had it on this slide first. There are 3 ways at which we can derive the Riemann-Christoffel tensor. We're only going to look at one of them, and we're not going to do a proper derivation, but just a picture, again, to try to illustrate how that derivation might come about. What I've said is, by parallel transporting a vector around a closed loop in our manifold, that provides a way to define the Riemann-Christoffel tensor. So how exactly does it do it? Well, this is where our picture helps. So here's a triangle. This is a triangle on a flat surface. It's got curved sides, but those curved sides are still embedded within a flat surface. Okay? So what we're imagining doing is parallel transporting a vector from A round to B to C and then back to A. And if you do that, then the vector will wind up back as a copy of the original vector. Maybe you can see that. So we parallel transport from A to B. So again, just our common sense definition of parallel works. You can see that this vector is parallel to that one because we're in flat space, and we can do the same down here, and then we can do the same there, and we wind up back with exactly the same vector. If we do this on a curved surface, so now, of course, I'm representing it on a flat screen, but I'm using perspective. You could imagine doing this with a globe, for example, or a basketball. If you take our vector now, and you parallel transport it from A to B, then the vector winds up pointing here, and then you parallel transport from B to C, it winds up pointing down, and we parallel transport from C to A. The vector no longer points in the same direction as when it started. So we can express the difference in the direction between the initial point and the final point in terms of the Riemann-Christoffel tensor. Yeah?
So, is there something special about the points themselves? Because we talked about parallel transporting as being keeping the angle between the vector itself and the tangent to the curve as constant.
Mm-hmm.
But if you look really close at one of those points, like, I guess I had confused myself before of saying, like, okay, the vector would like swing around the point. Like, do you have to say something about there's no tangent like at a point, or do you have to say, like, okay, we're going to parallel transport from A to B and then B to C and then C to A, as opposed to saying this is one long path?
Yeah, well, that's a good question. Again, let me give you a very brief answer. We'll maybe discuss a bit more over lunch. But what I think it boils down to is the way that I've drawn this, it's a closed loop, but it's continuous, but it's not a single differentiable curve, because, you know, basically as you go from A to B, you know, you change direction. So it's a closed loop in the sense that you wind up back where you started, but it's consisting of 3 separate curves, each of which is smooth. But so I think if one were to try to do this, I suppose there's no reason why you couldn't do it though, in terms of a closed loop that was nonetheless everywhere locally differentiable. I need to think about that one. Let's talk about it over lunch. I mean, the way I've set this up, the way that we usually set this up, is in terms of 3 separate arcs, and it's, you know, I think I've always felt that's quite helpful, because you can then, you know, break it down into what the arrow's doing along each one. But I don't think there's any reason in principle why you couldn't make it more of a smooth process, I think you would still get the same outcome. We'll try and draw it over lunch. Okay, so this actually relates a bit to your question. In a flat manifold, parallel transport doesn't rotate the vectors, while in a curved manifold it does. So that relates to your point about preserving the angle. So, this I think is a correct statement, and I think the way that I've chosen to represent that via the three arcs on the surface of the sphere doesn't violate that. But again, the purpose of this isn't to get tied down in all the complicated maths, but to give us a nice picture to visualize what's going on. And again, I borrowed this from a colleague when I was doing some lectures in the Virgo gravitational wave detector in Italy. And when the colleague was representing this, it was one of our Italian colleagues, thought a good way to think about it was in terms of parallel transporting the Empire State Building from New York to Rome. I don't think there's any serious plan to do that, but nonetheless, if you did, then basically the Empire State Building would not be pointing in the same direction because the Earth is not a flat surface. Okay, so I said that you can think of the Riemann-Christoffel tensor as being related to that rotation of a vector when you parallel transport it round a closed loop. So basically you can express the Riemann-Christoffel tensor, the components of it, and you can relate to that rotation. Algebraically, it looks messy. So again, we're going to shield you from as much of this as we can, but notice that it involves these Christoffel symbols. Maybe that's not surprising. The Riemann-Christoffel tensor is telling you what happens when you move around in a curved space-time, so it shouldn't be surprising that it depends on the rate of change of the basis vectors. So the Christoffel symbols, we relate to the rate of change of the basis vectors. You see lots of Christoffel symbols appearing in our expression for the Riemann-Christoffel tensor. You actually also see the derivatives of the Christoffel symbols. So that means it's going to depend on the second derivative of the basis vectors. Well, lots of things to do with gravity depend on second derivatives, so again, that shouldn't maybe be too surprising. But it's got a complicated mathematical form. We'd rather not spend too long staring at that.
Excuse me?
Yeah.
One question. To get a local sense of this curvature, we have to make this loop really small, right?
Yeah.
Okay.
Sure. And indeed, if you think of other ways that I might have done this that would have not gone fully into the tensor description, again, there wasn't time, but there's a lot of good textbooks that approach it this way. They ask questions like, what's the relationship between the radius and the circumference of a circle, where we define the radius as like, the arc length around the surface of the Earth. Like there's the center of my circle, and I draw a radius around it. Well, this is flat because it's very small, but if I was to do that with a circle that was 10 miles in radius, then actually I would, if I had accurate enough measuring equipment, I would realize that c doesn't equal 2 pi times r, and that's because you're starting to see the measure of the curvature. Now again, for a sphere, you can simplify it all down to just a single scalar number, which is the radius of the sphere, the radius of the Earth. But in general, it requires many more numbers to characterize that curvature. In other words, it requires the Riemann-Christoffel tensor.
So does the bigger loop give us like an average curvature sense of the what is in between, essentially? Yeah.
That's a good question. I'm not sure if that's a good way to think of it. Yeah. Again, let me come back to you now. I think at some level it must do. I mean,
Well,
if
you have a mountain right it's outside flat and I just draw around
Yeah.
it, it should give me
Sure.
because it doesn't
Sure.
know about that mountain.
it doesn't know about what's inside, yeah.
But if you had a mountain and a smaller like trough next to it, like you'd still get zero, even though the average wouldn't necessarily be zero.
Again, let's pick this up afterwards, if you don't mind. Just there's still quite a lot to get through, but these are good questions indeed. There are simple practical exercises one could do, and our colleagues in Western Australia have been trying to introduce some ideas like this, including that one about measuring whether the angles in a triangle are really 180 degrees, or whether the circumference of a circle is really 2 pi times the radius. They've been trying that out on primary school kids, just to kind of give them the experience of making the measurements and to gain some kind of physical intuition for how this all works. Obviously, if you showed them the tensors, it would blow their minds, but if they're just measuring, circumferences or measuring angles, they can handle that. Right, so with these excellent questions notwithstanding, what I've tried to say is that we have a way to describe the space-time curvature, that side of John Wheeler's little sentence, in terms of the Riemann-Christoffel tensor. What about the matter? Matter tells space-time how to curve. What do we use to describe that? Well, we use what's called the energy-momentum tensor, or stress-energy tensor. And again, there's a lot more detail in the longer notes. All we really need to do to get to where we need to be, which is heading towards a description of gravitational waves, is to come up with a simple expression for what that energy-momentum tensor would look like for what we call a perfect fluid. So that involves thinking about our distribution of mass in terms of little fluid elements, and they're all allowed to move independently of each other in general. But if we've got a perfect fluid, that poses certain restrictions on what the fluid elements can be doing. In particular, for a perfect fluid, there's no energy exchange between neighbours. They're not like rubbing against each other. That also would manifest itself as viscous forces, shearing of the fluid, where one fluid element is shearing with respect to another. Again, you can read the details in the longer version of the notes, but what it boils down to is that we can write the energy-momentum tensor, which is a 2-0 tensor, or rank 2, so it could be 2-0 or 1-1 or 0-2, but a convenient way to represent tensors of rank 2 is as a matrix. Many of you have probably come across that before. If you've done a course in special relativity, then you might have come across the idea of Lorentz transformations as a matrix. So I've written this as a 4x4 matrix, which we can think of as like the time and spatial components. And the 4 non-zero components for a perfect fluid of the energy-momentum tensor are rho, the energy density, and P, the pressure. All of the other elements are non-zero, and it's possible to show that the covariant derivative of the energy-momentum tensor, when we take its divergence, so that's noted here by the beta being in common, so that's the, you take the covariant derivative and then you basically sum that, you take the divergence, again just like, the divergence operator in language that you'll have come across before where we're talking about vectors, the div of x we would write as dx by dx plus, my notation's a little unfortunate there, capital X, small x, and dxy by dy, dxz by dz. So, in a similar way, this notation is summed, but it's also involving time, and this is essentially the relativistic version of the concept that we use in Newtonian physics as well, which is that energy and momentum are conserved. But energy and momentum, we need to really think about together in relativity, and again, maybe that's not surprising, because the components of momentum will appear to an observer who's moving with a particular relative velocity. But if you travel alongside a fluid element that's got a certain momentum, then actually in your frame now, it won't have any momentum because your velocities are matching. So what this really says is that in some frames, what one observer sees as contributing towards the energy, and other observers see as contributing towards the momentum, we can shift that balance around depending on which frame we're in. So rather than considering energy conservation and momentum conservation as somehow kind of separate concepts, what we really more appropriately think of is them as rolled in together in terms of this conservation of energy and momentum. In fact, there's a very nice introductory book called Space-Time Physics by Taylor and Wheeler. That's the same Wheeler of John Wheeler that we've talked about before. And in that book, they refer to mom energy as a sort of combined concept of energy and momentum together as being the conserved quantity. Right, so we're almost there. We've got the energy momentum tensor telling us something about space-time energy and momentum, the content of space-time and the matter and energy in it. And then we've got the Riemann-Christoffel tensor that says something about space-time curvature. But the Riemann-Christoffel tensor is of rank 4. What exactly does that mean? Well, notice there are 4 indices. I've happened to write it in a manner where I've got 1 upper and 3 lower. I could change that if I wanted, just using the metric to shift indices from up to down or down to up. But I still can't get away from the fact that there are 4 indices, whereas in the energy momentum tensor there's only 2. So it means that I can't immediately connect the 2, but what we do is we take what are called contractions of the energy momentum tensor. A contraction means that we sum over 1 upper and 1 lower index. So by writing the components of what's called the Ricci tensor as alpha gamma, notice what we've done is we've written a mu on the top and a mu on the bottom. So let me just briefly try and expand that out. If you haven't met any of this before, it does seem rather mysterious. So let me try and give a hint as to what's going on. I'll just keep the alpha gamma in, but that R mu, alpha mu gamma, what that basically is let's write it as alpha, I'll put 0 meaning the time component, plus R1 alpha 1 gamma, plus R2 alpha 2 gamma, plus R3 alpha 3 gamma. So we can write that equivalently as just R alpha gamma. These are known as free indices, so they can take any value 0, 1, 2, or 3, but we've summed over the upper index and the middle of the lower indices. We've summed those 4 terms together, and we've turned the Riemann-Christoffel tensor into a new tensor of rank 2 that we call the Ricci tensor. And the Ricci tensor, that means that we can now directly compare that with the energy momentum tensor because they're of the same rank. We can also, if we wanted to, and indeed it will prove necessary to do so, we can turn the Ricci tensor into a scalar. And what we do is we similarly do this contraction of the Ricci tensor with the metric. But this is the metric with upper indices. Again, if you want to delve into all the details of that, look at the longer version of the notes. What this gives us is something that's of rank 2 that we can compare with the rank 2 energy momentum tensor. But in fact, it turns out that the appropriate way to do that is not using the Ricci tensor on its own, but using something called the Einstein tensor, which is composed of the Ricci tensor and the Ricci scalar. Again, the details are in the longer notes or several of the books that those notes refer to if you want to wade through the algebra for yourself. But the really neat property, the sort of crucial physical thing that's going on is that we can show that the covariant divergence, so again that's summing over nu, covariant derivative, covariant divergence of the Einstein tensor, given by this combination here, that's equal to 0. But we'd already shown, well, we didn't show in these lectures, but it can be shown, and if you look at the longer version of the notes, you'll see the proof that the energy momentum tensor, its covariant divergence is also 0. So T mu nu semicolon nu equals 0, as does G mu nu semicolon u. Now I'm wearing this wonderful t-shirt that Chris designed for the Royal Society exhibition. Let's say that my previous attempts to design t-shirts weren't always so successful. When I was an undergraduate, I really liked doing GR, But that inspired us, our undergraduate class, to come up with a t-shirt that just said, T mu nu semicolon u vanishes. And we thought that was really cool to wear. Let's say that we didn't sell very many, but nonetheless, that's a really profound idea, because basically this is our John Wheeler statement now expressed in the mathematical language of relativity. The vanishing of the T mu nu semicolon u, the covariant divergence of the energy momentum tensor, and the vanishing of the covariant divergence of the Einstein tensor, well, if they're both equal, then one way to satisfy that is to have G mu nu equals K times T mu nu. And that, where K is a constant. And that is basically the solution to Einstein's equations that we're going to work with in the final 25 minutes or so to finally get ourselves a wave equation. So we can even determine the constant K by requiring that we should recover the laws of Newtonian gravity in the limit of a weak gravitational field. And we're going to look at a weak gravitational field. Later lecturers will go a bit more into the strong field domain, where we're looking at the generation of gravitational waves. But what I want to do is look at how a gravitational perturbation will propagate. And when it reaches the Earth, it's certainly going to be a weak gravitational field, but to demonstrate that we can describe that in terms of a wave equation. So K, we can work out, is equal to 8 pi g over c to the fourth. So remember something I said a bit earlier? I talked about space-time being incredibly stiff. Well, if you work out what that number is, you can kind of see why. 8 pi g divided by c to the fourth is an unbelievably small number in SI units. So what that says is that you've got to shake up space-time a heck of a lot with your T mu nu in order to produce a change in space-time curvature, G mu nu, that we could hope to measure, because this coupling constant is so incredibly small. So in other words, if I do this, I'm generating gravitational waves, but the T mu nu associated with me shaking my fist is not very big, and consequently the G mu nu associated with that is unbelievably small. And we really have to look to the cosmos as our laboratory to produce the kind of T mu nu's that would give us a chance of detecting gravitational waves. So solving Einstein's equations, even in exact form, is not trivial. Solving them when you've got perturbations, many of the subsequent lectures are going to be all about that, but I'm going to begin that process in the final 20 minutes before lunch. Let me just say, and I'm going to skip past these slides because there isn't time, I'd love to say more about this, but again, many of you will have encountered the Schwarzschild metric before, and if you've not, then you can find out all the details in my longer notes. But this is the exact solution that opens the door to a lot of the classic observational tests of general relativity. So it's solving for the metric for a particular case where you've got a single point mass, m, it's non-rotating, but what we're able to do is we're able to work out what the geodesics are. Again, the details are all there in the longer notes if you're interested. To compare those geodesics with what you would have for Newtonian gravity, and to realize that what that means is you wind up not with an ellipse for a single point mass, the sun, say, and a planet orbiting. Instead, what you have is an ellipse that precesses. The ellipse doesn't stay in the same place. And one can work through the algebra to see for one orbit by how much the ellipse precesses. E here is the eccentricity of the ellipse, would be 0 for a circle. A is the semi-major axis, m is the mass of the central mass. I've set g equal to 1 here. But basically, if you work out what that is, then you find that it's only 43 arc seconds per century, even for Mercury. But, as you'll see if you go through the detailed algebra, it's an effect that just keeps on growing. It's a secular term. It gets bigger and bigger and bigger the more often the planet orbits the star. It builds up. So that meant, because Mercury's been orbiting the sun for a long time, that even for the quality of observations that were available in the late 19th century, astronomers realized that there was a discrepancy in where Mercury should be if Newtonian gravity was the full story. Einstein's general relativity helped to resolve that discrepancy by explaining why Mercury wasn't where Newton said it should be. Much more dramatic example is the precession of, say, the binary pulsar system, 1913 plus 16, where the ellipse is advancing 4 degrees per year. So that's easily measurable. Similarly, if you look at the longer notes, we go through the derivation of light deflection. So we did it for a falling lift, falling elevator, in a kind of qualitative sense, but we can use the Schwarzschild metric to go through the detailed calculation. And what you find is that for a light ray that is just grazing the edge of the sun, because of the space-time curvature, that light ray will be deflected by about 2 arc seconds, or about 10 to the minus 5 radians. Now, when would you see that? You're probably aware that one of the famous stories in the development of relativity was that Arthur Eddington went on an expedition to try to see this during a total solar eclipse, when you can look at a star that's very close to the limb of the sun and see if its position is changed by the bending of the light ray, by the gravity of the sun, compared with when the sun is in another part of the sky. And basically GR passed that particular test. So that brings us to the final topic, our final 15 minutes. We're going to just race through some of the key ideas that will give us the wave equation for gravitational waves. Okay, so we've talked about gravitational fields and how we can describe the effects of that gravitational field in terms of space-time curvature. We also did a little calculation that wasn't very rigorous, but it was to try to give us the sense that the local gravitational effects at the Earth are actually rather weak compared with, say, the equivalent calculation for a white dwarf or for a neutron star. So that gives us a sense that there must be a way that we might think about a weak gravitational field. So let's try and do that a bit more rigorously now. We've now got the idea of a metric under our belts, a set of functions that describe the interval between space-time events. And we could write the metric as the metric of Minkowski space-time, flat space-time, the metric of special relativity, plus an extra piece, h alpha beta. So if h alpha beta is very much less than 1 for all of its components, then we can regard our space-time as nearly flat. Okay, because remember the eta alpha beta components, they're all going to be of absolute value 1, either minus 1 or 1. So if the h alpha betas are all very much less than 1, then that means that they are relatively unimportant compared with the eta alpha beta components. So we could call the coordinate system that describes such a metric that we use to plug into that metric, we could call that as a nearly Lorentz coordinate system, because it's nearly described by the metric, the Minkowski metric of special relativity. But we need to do a bit more than that. We need to have the means to take our nearly Lorentz coordinate system and then change our coordinates and look at what effect that might have. So if we find a coordinate system in which space-time looks nearly flat, then there's certain coordinate transformations we can carry out and it will still look nearly flat. And that's good, because remember, we need to be able to formulate our laws of physics in a way that's the same for any coordinate system. Well, maybe this is going to restrict us to certain classes of coordinate system, but at least we want to be reassured that our laws of physics can be described when we transform to one of those classes of coordinate system. So there's two such examples I will very briefly mention. One is called a background Lorentz transformation, and that's quite simply this. If you've got a space-time that looks nearly flat to one observer, then it's going to look also nearly flat to any other observer who's in uniform relative motion with respect to the first observer, provided they're not moving too close to the speed of light. And then the second one, this is a more subtle one and a bit harder to get your head round in a rushed final 15 minutes. But again, all of the details are there in the longer version. But think of it like this. If you've got a coordinate system in which space-time looks nearly flat, then you can tweak the coordinates. You can adjust them a little bit by a small amount, what we call a gauge transformation. You can add an arbitrary small vector to the coordinates x alpha. So x alpha goes to x alpha plus psi alpha, and it will stay nearly flat. So you can choose the components psi alpha to make Einstein's equations as simple as possible. That's kind of one of the reasons why we refer to this as gauge transformation. It's links back to the use of that terminology in fields like electromagnetism, where your choice of gauge can simplify the equations. So that's what is involved. There's a huge amount of complicated algebra coming up in the next slides, but all you really need to take away from this final piece is that we've got Einstein's equations to begin with, and by suitable choice of coordinate system, we can simplify Einstein's equations. And that's what we're going to do. So for example, if we have a nearly flat coordinate system, a nearly flat space-time, then the Riemann-Christoffel tensor for a weak field can be reduced to this. So what is this? So the H's, remember, those were the extra pieces added on to the Minkowski metric. Okay, so you can think of those as like a perturbation to flat space-time. And this expression just involves the second order partial derivatives of those terms, but it involves different combinations of the components. So sure, you can wade through all the algebra. There isn't time to do that. Life's too short to kind of do all that on the blackboard, but if you want to go through the lengthy version, it's all there in the extended notes. But once we've got a Riemann-Christoffel tensor in this simplified form for a weak field, then we can do the same with the Ricci tensor. We can get an expression for that. And I've introduced some rather odd-looking notation, basically just to do with raising and lowering indices. Again, don't get hung up in the details, because most of those terms we're going to make go away in just a moment anyway, by appropriate choice of gauge. But as I said, lots of messy algebra to contend with. We get this very messy expression for the Einstein tensor, but we can introduce a neat trick to simplify that. And what we do is we take our perturbation h mu nu and we make a new version of it, h bar mu nu, by subtracting off this term. So a half eta mu nu is the Minkowski metric, and just an h, that was defined on the previous slide. H is, think of it like the trace of a matrix. What you're doing is you're adding up the diagonal terms of a matrix. That would give you the trace. Well, this is very much like that. And the name is sort of appropriate because in just a few minutes, we're going to do something that involves choosing, we call the transverse traceless gauge. And as the name suggests, traceless means that the trace equals 0. So that means that h is 0. So actually h bar mu nu and h mu nu are the same thing anyway. So it's one of those neat examples of where the mathematical trick is to introduce a term which you later show to be 0 anyway, but by introducing it, it simplifies the equations. So what all of this does is lets us get rid of these last three terms by choosing what's called the Lorentz gauge and using this h bar form. And in the Lorentz gauge, in free space, which means that the right-hand side t mu nu equals 0, it's possible to rewrite this weird-looking thing in terms of something that looks much more familiar. This is called the D'Alembertian, or wave operator. So this expression, using the Einstein summation convention and the partial derivative operator, actually, if we now rewrite that back in more familiar, explicit partial derivative notation, what we get is minus d2 by dt squared plus nabla squared times h bar mu nu equals 0. And all of this was done in the case where we assumed c equals 1, just to simplify the equations a bit. But now let's put c back in. If we put c back in, then we get minus d2 by dt squared plus c squared nabla squared h bar nu equals 0. And this really is the key result. I've still got a few minutes left, so I'll go on just a couple more slides, but this is the place where I wanted to make sure I had got to, because this is a wave equation. What this says is that those metric perturbations, now these are admittedly the modified form, the h bar mu nu, but the modified form of the metric perturbation satisfies a wave equation. And not just any old wave equation, it's a wave equation that propagates at the speed of light. And it's not accidental that it propagates at the speed of light. The c comes about because it's hardwired into the Minkowski metric. It takes us all the way back to the special role that the speed of light plays in the development of special relativity, which again, without wishing to be too patriotic, I was linking back, just as Einstein did himself in the 1905 paper, to the seminal work of James Clerk Maxwell. So the speed of light finds its way into special relativity and then general relativity and then eventually explicitly into this wave equation. So it is a clear prediction of general relativity that gravitational waves, these h bar mu nu terms, should propagate through the vacuum at the speed of light. Okay, we're almost done, but that h bar mu nu, in principle, could be, even if we impose symmetry, which says, h bar mu nu has to be the same as h bar nu mu, the 1, 0 component has to be the same as 0, 1, and so on, that still, in principle, allows up to 10 free parameters. We'd like to reduce that. So I just want to zoom through what, again, is there in explicit detail. I nearly said exquisite detail, but that's a bit presumptuous. It's for you to judge whether it's exquisite detail, but I've tried to make the longer version of the notes as clear and complete as possible, but I can't possibly, in the final few minutes, cover all those details. But basically, what we do next is we try to get those 10 independent components, which symmetry turns 16 into 10, to see if we can knock some more off, if we can exploit some properties to take it further. Firstly, it's quite straightforward to show. Again, look at the longer notes if you want to see why. That the wave vector, so what I should have said that we're going to do is we're going to represent these as plane waves. So our disturbance, our perturbation, we could decompose into a series of plane waves. I'm just going to consider one, but you could replace this by a sum if you want. The real part of our complex expression. So we've got wave amplitudes, we've got wave vectors. And straight out the bat, we can show that the wave vector is null. So that contraction k alpha equals 0. And then we can start to link this more explicitly to an actual physical system. So let's suppose we orient our coordinate axes so that the plane wave is travelling in the positive z direction. And let's call kt, the time component of the wave vector, let's call that omega. Kx, ky are 0, and then kz is going to be omega as well because it's a null vector. And that also means that A alpha z is going to be 0 for all alpha. And that essentially means then that there's no component of the metric perturbation in the direction of propagation of the wave. So the disturbance, the metric perturbation, is perpendicular to the direction of propagation. It's transverse. And then we choose a gauge. I think you'll have to look at the longer version. I think I've left a slide out that I meant to put in, which was to demonstrate that h bar equals h. I'm just assuming that here, but it is demonstrated in the longer version that when you assume the coordinate setup that I've described here, then in fact what it does is it imposes the condition that the scalar quantity h that I said you can think of as like the trace, that basically that winds up being 0. So again, apologies for leaving that slide out, but kind of almost out of time anyway. Essentially, there's sufficient symmetry now to knock out everything but 2 terms. So what we've got is AXX, that has to equal minus AYY because it's got to be traceless along the diagonal. And then we've got also an off-diagonal term, AXY. All the others are 0. So I'm going to run over by just a couple of minutes, but I just want to get to the point where you can all see what would happen to some free particles as this gravitational wave comes along. So the key thing that is explained in a bit more detail in the longer version, and I'll just have to say almost nothing about, but to emphasize at least the key point, which is that we really need to measure the proper distance between neighbouring particles. If we just consider the spatial coordinate separation, then that actually doesn't change because the coordinate system adjusts itself as the gravitational wave passes by. So the meaningful physical quantity is the proper distance between neighbouring particles. Now we know how to work that out. We work that out again in terms of the metric. Again, I don't think I went in sufficient detail this morning in the lectures to let you see where that comes from, but look at the longer version of the notes and it's all there. So what we find is that the proper distance actually does change in time. So here we're considering 2 test particles, one at the origin and one at coordinate distance x equals epsilon, y, z equals 0. And we get this expression for how that proper distance changes, and in general that's going to vary in time because this term here is in general non-zero. And in fact we can now think of doing that for a ring of particles all the way around the ring, and in general what we get then is an equation for how the x separation changes and how the y coordinate separation changes. Remember, it's transverse, so the wave is propagating in the z direction, so we only really need to consider what's going on in the x and y. But look, this is what happens. We start off with a circle of test particles, and as the gravitational wave propagates because of the sinusoidal variation in the hxy, hxx in this case, then we get this pattern. Because I'm standing at the side, I'm thinking I'm already onto the cross polarization, but if I stand in line with it, I'll see that it's what we call the plus polarization, because the stretching and squeezing is aligned with the x and y axes. Whereas if it's the xy term that's non-zero, then that's what we call the cross polarization. The stretching and squeezing is now at 45 degrees to the x and y axes. And I think that's probably a good point to finish. There are a few more slides. There's certainly plenty more material in the longer version of the notes. And I didn't really think I would have time to get onto this, but you might find it interesting to look at the slides for yourself. It overlaps a bit with material that others will cover anyway, but I think what I seek to do here is to basically give you a handle on how big we would expect the gravitational wave amplitude to be, how it depends on frequency, and how it depends on distance. And this is for the case of 2 point masses, like say 2 neutron stars or 2 black holes orbiting each other. So I won't go through that now, because again, that story will be picked up by others. But I can highly recommend, in any case, just in case some others don't cover it, the following paper that the LIGO and Virgo collaborations put out last August. And this, I think, is a really nice way to try to get your head around the basic physics of the first detection event using as little general relativity as possible. So if there's time in the panel discussion, I think Sathy and I, we've got an hour sort of Q&A. If we run out of questions, or if I plant a question that you might ask, if you ask about this paper, then Sathy and I will discuss a little bit how this paper shows, crudely, and it's not a rigorous derivation at all, but it's a really nice illustration of how just using Newtonian ideas, you can go a long way towards understanding the physical properties of this system. And I think it's well worth looking at that paper. However, from here on in terms of how these GR ideas are taken forward, and I hope for those who'd not met any GR before, that I've given you enough confidence that the remaining time in the 2 weeks isn't going to be completely unintelligible. And certainly, please do with those lecturers, as some of you have done with me this morning, please talk to them, ask questions, interrupt them, make sure that you don't sit there for ages worrying about what something means or what it represents. Ask the lecturers, and I'm sure they'll be very happy to try to explain. With that, I shall stop, and we shall all hopefully go for lunch. So thank you very much.